Okay, starting in section 5.1, we're going to talk about something called coordinate vectors. So we have a definition written down here. Let B be an ordered basis, and that means that the order of the basis is going to matter for reasons that we'll get into in a few minutes. The coordinate vector of a particular vector V is a column vector where the constants in that column vector are the constants in the linear combination. How would you write V as a linear combination of that basis? Okay, that's a little bit of a mouthful. We'll come back to that after we've seen an example. So let's try and find the coordinate vector of 3x squared minus x minus 9 relative to the standard basis. So in order to do that, I need to find, how do I write this as a linear combination of these vectors? So I have to write v, which is 3x squared minus x minus 9, as a constant times x squared plus a constant times x plus a constant times 1. We should be able to just kind of see what the answer is going to be. Coefficient in front of x squared is going to be 3. Coefficient in front of x is going to be negative 1. And the coefficient in front of 1 is going to be negative 9. And so our vector, our coordinate vector for v relative to this basis is VB is a column vector 3, negative 1, negative 9. Okay, so I kind of let the cat out of the bag there. I said the words relative to a basis. I already wrote it down, relative to a basis. The idea is that if we have different bases, we might describe this vector in different ways. So let's do the same example, same vector, only a different basis. So let's try that out. So relative to this basis, which I'm calling the B prime basis, I would still have to find the linear combination. 3x squared minus x minus 9 is equal to a constant times x squared plus x plus 1. Guess I need parentheses. Plus a constant times x squared minus 5 plus a constant times x plus 2. Okay, if I distribute this all out, our x squared term is going to end up being, let's see, c1 plus c2 is equal to 3. C1 plus c3 is our x coefficient, and that's supposed to add up to negative 1. And then c1 minus 5c2 plus 2c3 is going to be negative 9, my constant, which means we're really talking about solving an augmented matrix 1, 1, 0, 3, 1, 0, 1, negative 1, 0, 1, minus 5, 2, minus 9. Okay, so then we would row reduce this. And if you just type that in a calculator, you get first row 1, 0, 0, 2, second row 0, 1, 0, 1, and third row 0, 0, 1, negative 3, which tells me that this is my C1, C2, and C3. Okay, so we've solved for our constants, and so we should be able to write the coordinate vector relative to this other basis, the B prime basis, which is going to be 2, 1, negative 3. Okay, so writing the coordinate vector of the same vector relative to a different basis is going to give us a drastically different answer, 3, negative 1, negative 9 versus 2, 1, negative 3. And I'm going to go all the way back to the original word I was emphasizing in the first line. An ordered basis is because the order in which the vectors v1, v2, and so on appear is going to tell us the order in which the constants appear. So for instance, if our basis instead of being x squared x1 was 1, then x squared, so increasing order, we would have to change the order the constant showed up. And so instead of having the vector 3, negative 1, negative 9, we might have the vector negative 9, negative 1, 3. So the order matters, and also which basis you're using is going to matter. Okay, I'm going to pause and pull out another example. Okay, this example is actually trying to find a coordinate vector relative to an orthonormal basis. And it turns out, because of the magic of projections, that's going to be even easier than finding coordinate vectors or finding a linear combination normally is. So it turns out that all we have to do is take a dot product with each of the corresponding vectors. So our constant C1 is just going to be the dot product of vector 1, dot product of v with the first vector 1, 0, 0, which is actually just going to be the number 1. And our second constant is going to be v dot product with the second vector, which is 0, 3 fifths, 4 fifths. And so if you do that dot product, first component multiplies to be a 0, second component is 6 fifths, third component is 12 fifths. And so we end up with 18 fifths as our second constant. And then same thing for C3. Just really quickly, let's write that one down. 0 minus 4 fifths, positive 3 fifths. And this is coming from some formulas or some theorems we had when we were originally looking at orthonormal. And so we end up with solving the constants very, very quickly. We don't have to solve a system of equations, it's just some dot products. And so what we end up with is that the coordinate vector of v relative to this b basis, this orthonormal basis, is just going to be these three constants, 1, 18 fifths, and 1 fifth.